It's really a pleasure to be here and to talk to you all. And I really hope that I can give you a kind of introduction to what is a really awesome field of machine learning right now, and scientific machine learning, which is physics-informed neural networks. So I wonder if you could use the chat and just raise your hand if you can. I don't know if you've enabled that, Jousef, but if you've ever heard of a physics-informed neural network before, that would help me to get the right level of the workshop. So just put your hand up in the chat if you can. Okay, so it seems pretty fresh to, yeah, there's a couple of people, but it seems fresh to most people. So that's great. So hopefully I'm going to show you a new tool that you can go and take away for the future. Okay, so what does this workshop look like? So I've got it's split into two. The first section will be very quick, maybe 10 minutes or something. And then the bulk of this workshop is me doing a coding session. And I'll send you, well, you can see there on my GitHub, Ben Moseley harmonic oscillator PINN workshop. You can go to that right now and look at, download the code and even go through it with me if you want to as well. But it's not necessary. If you can just watch me code if you like as well. So the first part, I'm just going to introduce PINNs, tell you what they kind of use for at the moment, and kind of their pros and cons compared to traditional methods that we use instead. And then, yeah, I'll go into the demo. We'll code a scratch based on this harmonic oscillator example, which I'll talk about more. And then I'll give you some ideas of how you can extend it to more kind of advanced tasks as well. So yeah, let's first kind of motivate PINNs. So what are they? Why are they useful? How did they come about? So first of all, I'm just going to talk about doing science in general in a very kind of abstract way. I think it helps you to kind of understand why PINNs are useful. And so at the risk of generalizing too much, I would argue that a lot of science, or the tasks that we do in science, can be kind of broken down into kind of three big areas. And I've listed them here. So one is forward simulation. And this is where we have some system, scientific system, physical system that we want to simulate. And by the way, here I've given an example of modeling earthquakes. So kind of waves and solving the wave equation, that sort of thing. But this can be applied to any kind of physical system, be it fluid dynamics, molecular systems, anything really. So yeah, the first task is to carry out forward simulation. So it's given some initial conditions of the system. Can we simulate the evolution of the system in time or in space? The second one is inversion, and this is where we're actually given some of these observed parameters. So for example, if we measure an earthquake, we measure the displacement on the surface of the Earth. And we do that with kind of seismometers in the ground. So an inversion task is, given these potentially noisy observations, can we actually estimate the underlying physical parameters of that system? And in this case, it would be the structure of the Earth and the location of the earthquake. And then the kind of final task is what I would call equation discovery. And this is kind of like real kind of first principles physics, like given all of this information, the observed data, maybe we know the structure of the Earth and where the earthquake came from. Can we actually understand the underlying equations, differential equations, in this case, the wave equation that produce that data? And so, yeah, so many kind of scientific tasks can kind of be grouped into these categories. But of course, there are many, we spent tens of years, hundreds of years investigating these types of tasks and the techniques for solving them. And clearly they're very complex depending on the problem and the domain. And kind of some of the biggest challenges are incorporating more complex phenomena, kind of multi-scale, multi-physics systems. These are often very difficult to compute. For example, inverse problems can be very ill-posed and take a lot of effort to run a simulation. And then we have to deal with real-world noise and data as well, which can be sparse and noisy. So, okay, so let's switch it up and talk about, given that these tasks are really hard, but still really important, over the last 5 years, 10 years, people have really started getting excited about using machine learning to help accelerate and improve those tasks. So here's my single slide on deep learning, which is 99% of the research is using deep learning to solve these tasks. And so what is a neural network? It just takes in some input tensor or matrix or vector, passes it through a neural network, which is just a series of mathematical operations, for example, just timesing by weights and putting through an activation function, then adding a bias, and then giving an output. And we train it using gradient descent and appropriate loss function and lots of data. But the key thing is that it really just is a mathematical function, and it's kind of flexible function fitting. And I know machine learning can get way more complex than that, but this is how I try to think of it as a physicist. So we can apply neural networks to try and solve these types of tasks I was talking about. And this is a paper that we did where we're trying to do exactly what I was describing, trying to simulate seismic waves through the Earth. And you can, what we started to do in science was to train these in a very naive way. And what I mean by naive is the algorithm itself wasn't informed by any physics, and we just generated lots and lots of, like, millions and millions of training data, and then we put a neural network in the middle and just tried to learn the mapping between the two. So, for example, here the input to the network is a velocity model, and the output is the predicted pressure or the predicted displacement of the Earth. Or pressure, actually, a set of receivers on the surface of the Earth. And I just made millions of finite difference simulations to get this training data. And the result is that, as you probably would expect if you know about machine learning, the neural network performs well when I give it a velocity model, like an input that's close to its training distribution. But as soon as I give it a velocity model that's outside of it, so one that's got more complex curves or faulted structures in it, the performance really degrades. And this is a major problem. This idea of generalization is a really hard problem to solve, and so what that's spurred on in the last 2 years, 2 to 5 years, I would say, is this new field, and it's called scientific machine learning. And the whole idea of the field is, well, we recognize that we have kind of issues with the interpretability, the generalization, and large amounts of training data that we need for neural networks. And so, and it's not really satisfying to say we're just going to throw away all this existing science and physics knowledge that we know already. Why don't we just combine physics and machine learning together in more nuanced and principled ways? And hopefully that will produce more interpretable and more powerful models. So I think this is a super exciting field, and there's a lot of stuff going on towards this idea. So, for example, there's been workshops. Some of the key papers for specifically physics-informed neural networks. This number of citations has been growing massively, and there's been a lot of money that's been put in. For example, this IAIFI lab in MIT, trying to combine fundamental physics and machine learning together. I'm going to skip over this very quickly, but in my PhD thesis, which has just come out, I really encourage you to have a look if you're interested in this more generally. I tried to cover all these different techniques in scientific machine learning that are coming out today. And so PINNs are just one of these techniques, but you probably recognize some of these, like Fourier operators, depot nets, AlphaFold can be thought of as scientific machine learning technique, et cetera, et cetera. So, okay, so I tried to motivate scientific machine learning, and I told you about the important tasks. So now I'm going to tell you about that specific tool that we're going to look at today, which is physics-informed neural networks. So how do they work? So the main idea is, can we put physics principles or understanding of the physical system into the neural network when we're training it, so that it understands kind of physics compared to a network that's just trained naively. So the way to kind of explain this is, just imagine that we have some physical process that we're trying to model, and we have these kind of orange dots here of the process. And so one way to do it is just to have a neural network and say, okay, we have some training data, we're going to try and fit the neural network to model these points from this physical process that we're not sure what it is. And so you would just train the network in a very standard way by minimizing the difference between the network's prediction and these true experimental data points that we have. This is just the mean squared error, a very standard way to train your network. And you can see if you train the network, it does very well inside the experimental data points, but outside the performance of the network really degrades. And this is exactly that generalization problem that I said at the start of the presentation. So it really doesn't understand, even though from the data you can see it's kind of oscillatory, the network's not getting that in further examples. So the point is, in physics and in science generally, we have some prior understanding of what's going on. So if I told you that this is actually from a harmonic oscillator, so these points here are measurements of the displacement of this square box, this green box here, as a function of time. And so this oscillator is damped, and so the amplitude of this oscillation decreases over time as well. And so we know exactly what the underlying differential equation for this is. Just a combination of its second order and first order derivatives with these parameters, which is just the mass of the oscillator, the coefficient of friction, and the spring constant K. So PINNs are very, very simple, and the whole idea is basically to add this underlying differential equation as an extra term in the loss function and make sure that the solution that the PINN learns matches that underlying differential equation. So it's a very simple idea, but very powerful. And so you can see on the right here, we have now a loss function which has two terms. The first term is that we're matching the PINN to these observed experimental points. And then the second term is new. And what we're saying is we want to compute various derivatives of the PINN with respect to its inputs, and then combine them together so that those derivatives evaluate the residual of the underlying differential equation. So you can see in a perfect world, if the PINN knew the solution exactly, this last term would be 0 because the underlying differential equation would be obeyed. But in general, it's not. And so this is something that we can optimize over and try and improve the solution of the PINN. And so the only other thing that we need for this second term, we note that we don't need any data, any example data, any additional data. The only thing that we do need is we need to evaluate the PINN a few points in the random points, or maybe regular points in the domain where we can evaluate this physics loss over. And so you can see the green dots on this image here. So we're also to evaluate the physics loss, that's where we're evaluating the loss over. And so if we choose these green dots that are further away from the experimental points and minimize over the PDE loss, then we start to learn the full solution and all the oscillations in this example. So that's how PINNs work in general. I'm just going to pause for questions. Has anyone got a question on this before I move on?
Hi, I have a question. So what if you have external force? How would you model in that case?
Yeah, sure. So external force might come up on the other side of the equation, for example, as like a source term. So all you would do is you would just make sure that you would just move that source term over to the left-hand side of the equation so that the whole thing equals 0. And then you would just essentially just add it in this bracket here, and that would be included. Does that make sense?
Yeah, thank you.
So yeah, that's a good point. I've shown you for the harmonic oscillator here, but PINNs are actually a very general framework in that you can do this to any PDE, and they have been applied to many, many different types of PDEs. So this is why they're such, I think is why they're such a powerful technique and such a popular technique right now.
But you'd have to be able to stare at in this case, the physical phenomenon that you're dealing with in order to determine this part of the equation that helps the function work. What does that say about sort of the self-defeating purpose of the neural network part. If I already know the function behaves this way, then, well, why don't I just use the function for the entire equation?
Yeah, good point. So for this example, I've chosen a basic one just to tell you how it works. But of course, we know the answer to the differential equation here. It's just cos omega t times by an exponential function that is such that it decays. But I mean, in general, so it's not very useful for this problem, I agree. But in general, we don't know the solutions to more complex differential equations. So for example, Navier-Stokes, or even the wave equation. And so one way you can think of PINNs is they offer a kind of new or different way of solving differential equations and carrying out simulation.
Thank you.
Yeah. So another question you might ask is, well, we have to know the underlying differential equation to start with as well. But actually, it turns out you can start to learn that as well using PINNs, and I might get onto that too. Okay.
So just one quick question, like how do you determine like at home this, so for these physics laws training locations, so is there any like how does it affect the solution, like how many number of points you are going to add to that?
Yeah.
Does it have any dependence?
Yeah, so there are a lot of kind of hyperparameters that you have to choose when you're training PINNs, and kind of the density of the points or the location of the training points is definitely one of them. I don't think there's a good answer right now for kind of how many you need or their distribution. And actually in the research, people are doing a lot of kind of different things. So you can do random sampling. You can even do kind of intelligent sampling where you kind of evaluate where the solution is not very good. The way, I don't think there's a really great answer for it, but the way I like to think of it is like, it's a bit like finite difference modeling, where if you choose a very coarse time stepping or like grid size, then the solution might not be very accurate. And it's kind of the same with PINNs in a kind of wishy-washy way.
Okay, sure, thanks.
Okay, I'm going to move on so that we have time for the coding. So just a quick example of PINNs. So we did this with the wave equation. Again, trying to solve, given this starting solution of the wave, so at time equals 0 in this red box, we have like a circular wave in the middle here, and we want to model its evolution in time through this kind of layered velocity model with different velocities in each layer. And so the PINN is just, like I said, it's a neural network. And the inputs to the PINN are just the X and the Y positions, and then the time. And then the output of the neural network is the prediction of the physical quantity that we're trying to model, which in this case is the pressure of the wave field. So you can see these are not like images or even matrices or vectors. They're just kind of 3 single inputs, 3 scalar values that we're inputting in 1 scalar output. And of course, you change this to whatever PDE you're interested in. Then so I didn't mention, but when we're evaluating this physics loss, we need to evaluate the gradients of the neural network with respect to its inputs, so its time derivatives and its spatial derivatives. And so the real beauty and the real enabler of PINNs, I would say, is the fact it is auto-differentiation, and the modern deep learning packages like PyTorch and TensorFlow allow you to very easily compute these gradients, and also differentiate through them again to update the weights of the neural network. And so we don't have to hand write all these gradients down, which would be a very difficult thing to do. So this is very, very, very powerful. And then given those quantities, we just compute our 2 different loss functions. In this case, the boundary loss here, or the training points that we have are just the very first time step. And then the physics losses evaluated over the entire domain over all times. And so you can see the PINN is this 3rd row here. You can see, even though it's only given data from the first time step, because it has this physics loss further out, it can start to measure all these complexities of the dynamic of the wave. So it's squashing and expansion in different velocity regions and reflections as well. So yeah, really, really impressive to see PINNs working for like a complex wave.
So just a basic question again, it has nothing to do with the actual PINN, but how is the output so rich in the visual when you said that there was one number on the other end?
Right, yeah. So the way that you create these kind of plots or like simulations is even though the pin takes a single like coordinate as the input, you can just batch them up, right, and just give the neural network like 1,000 points on a grid, and then it will just give you the solution.
Oh, okay, got it. So you're plotting. Is that the pressure? Is that what it is?
Yeah, this is the pressure of the.
You're plotting the pressure against this coordinate.
Exactly.
Okay.
And I'm just showing it as the inputs that I choose are on a grid. They don't have to be, but for me, just to plot an image, I've just gridded it. So yeah, but this is an important point that the neural network is actually this whole thing here is a functional approximation to the solution. So this is again is a bit different to how you might have done neural networks in the past, where it tries to learn like a discretized representation of your solution. So like the solution on a grid. This is actually a function, so it's continuous. That's an important thing to realize as well. Okay. So pros and cons. I'll quickly cover this, and then we'll get straight into the demo. So what are the pros of cons? So I've just showed PINNs for simulation at the moment. I haven't talked about any of the other scientific tasks. So what traditional methods do we have for simulation? We have some of the big ones are finite difference modeling and finite element modeling. So if I'm just going to do the pros and cons compared to those two techniques, this is kind of what it would look like. And so finite difference, finite element modeling is actually you need to discretize your solution, and you need a mesh typically to run those simulations, and it can be very challenging to define that mesh. So PINNs, like I said, they represent the functional solution, and so they're actually mesh free. I don't need to create a mesh to train them. They're mostly unsupervised compared to kind of naive neural network methods where you need a lot of finite difference simulation training data, which is great. And I'll get onto this, but they work very well in these kind of mixed regimes where you actually want to learn something about the underlying differential equation as well. But cons is that we don't really understand the convergence properties of PINNs very well at the moment. There's a lot of theoretical work going on, but it's still not, if you compare that to finite element methods, finite difference, where they're very well understood, it's very hard to understand. Also, the computational times, if you just want to train a neural network to do a forward simulation, it's not competitive compared to finite difference simulations. So if I go back to the wave equation here, this actually took 3 hours to train, whereas like a finite difference solver would take like 30 seconds. I didn't really optimize this, but it kind of gives you a feel. And then the final thing, which probably we won't get onto, but they often struggle to scale to more complex solutions, just like finite difference solvers would as well. So there's no super free lunch, but you can see there are differences to traditional methods that we can kind of use if we use them well. Okay.
So the cons are really around a little bit of a cost, but and then the fact that it's not explained, right? The explainability of it all on number one, I suppose. But in general, ultimately you have to use these physics-informed networks. I mean, if you know that it improves the accuracy and precision, blah blah blah, then would you say this has to be done at some point? I mean, this is inevitable. Is that sort of a thought process or not?
Oh, this is it would be great to see PINNs being used for every kind of simulation and inversion task. For that, there are big hurdles. I think this kind of poor scaling to higher frequencies and more complex solutions, that is a really hard challenge I worked on in my PhD, if you're interested. So I think they're not competitive right now. I don't think they're competitive with forward simulation, but for these inverse tasks where you have some data, you want to learn something about the PDE, I think for sure they can be competitive. I have an example of that in the notebook coming up. But yeah, this is a very interesting area that could definitely help the traditional difficulties we have with simulation. Okay, so let's get on to the demo then. So like I said before, it's on my GitHub if you want to look at the code. Harmonic oscillator PINN workshop. And so we're going to be coding a PINN to simulate this harmonic oscillator example that I showed right at the start. So I'm just going to switch screens. So I'm going to stop sharing very briefly. Then I'm going to share my okay, so hopefully now you can see a Jupyter notebook. Just let me know if you can see that all.
Yep.
Great. Okay, so in the repository, so we've got maybe another half an hour. I'll go through this example and then some more time for questions. Again, feel free to interrupt me if what I'm doing is confusing you or you just don't follow it at all. So inside that repository, there are actually two notebooks. There's one called PINN Intro Workshop. Just to check, you can see my my cursor. Is that okay?
That works, yeah.
Yeah, cool. So there's one called PINN Intro Workshop, and then another one, PINN Intro Workshop _student. And the idea is the student one, which I'm looking at right now, has a bunch of cells that are blank. So if you really want to learn how to do it yourself without looking at the solution, I recommend having a go on this one first. And then if you get stuck, you can always look at the solution notebook as well. Yeah, so we got a couple of goals with this task. The biggest one is that we want to be able to learn how to code a PINN from scratch. Then we want to understand a bit more, how can we adapt the PINN to different scientific tasks? So can we do simulation? Can we do inversion? We'll cover both of those in this example. And then if we get time, we'll try and figure out how to improve the PINN's convergence. And there are many tricks that you can use to kind of improve how PINNs work. And how this example scales to higher frequency oscillations as well. That's an interesting question. So the environment should be very, very simple. I'm going to assume that you understand kind of basic Python and basic PyTorch, and that's what we're going to be using. So I'm not going to talk about exactly how to set up your environment, but it should be very simple. You just kind of need these Jupyter, NumPy, Matplotlib, and then PyTorch is the platform that we're going to be using to code it up. So yeah, we're just going to import all of our modules here. So this is the problem overview. Like I said, we're going to try and get the PINN to model the solution to this harmonic oscillator. As I explained before, we have the underlying differential equation here. And what we're going to get the PINN to approximate is the solution to the differential equation, so the displacement of this green box with respect to time. So there are actually a couple of different solutions of this system, depending on the values of the mass, the friction coefficient, and the spring constant. So we're just going to focus on this underdamped state, and this is where there is some oscillation, but it's just slowly damped in time by friction. And this occurs when these quantities here are under this condition and computed by these equations. I'm not going to get into detail the maths behind this, but if you're interested, you should have a look at this blog post. It goes fully through the derivations of the different solutions. But here's basically the final solution of this system, and it's just the displacement as a function of time. It's just this cos omega t times by this exponential function here, so this exponential decay of the oscillator. So this is just the equation for this gray line here. So we're going to try and get the PINN to learn this without knowing what the solution is. And the only other thing is to make sure that this solution is unique, a particular solution of the differential equation, we have to assert what the initial conditions of the system are. And so what we're going to say is the oscillator is at displacement 1 when time is 0, and its velocity, so the derivative of u with respect to t is 0 at 0. So you can kind of see it starts up here at the top of this sine curve. Okay, so hopefully that makes sense. So we're going to cover two tasks here. First, we're going to use the PINN to simulate it, given the initial conditions, so exactly as I talked through before. And then we're going to try and do a different task, which is to try and invert for some of these underlying parameters. So this is we're going to try and invert for the coefficient of friction here. Given some noisy observations of the displacements, we're going to assume we have a bit more observations to deal with. And then if we get time, we'll have a look at how it scales to high frequency oscillations and see what we can do to improve it. So there's a couple of just kind of setup Python functions here. So the first one is just defining what the exact solution is so that we can compare the PINN to. And so it just takes in these two constants here and a time array, and it will tell you what this solution is. And then the second class here is just it's just defining a very standard fully connected neural network in PyTorch. There's nothing fancy going on here. But we're going to be using this as our base neural network to train. So you see, we're just setting up a bunch of linear layers here. We have a tanh activation function here, and the forward pass is just the combination of those. Okay. Any questions up until here, or does this make sense to you? Okay, silence is a good thing, hopefully. All right, so first task, train a PINN to simulate the system. Okay, so let's think about the inputs and the outputs. So, oh, hello?
Yeah.
Okay. Yeah, go on.
No, I just wanted to confirm that the additional information that the data science person or the individual that's coding this is in the loss function part, which is calculated where, or is defined where in this section here?
Yeah, so we're getting onto the training loop. That's what I'm going to be coding in a minute. So this is just a bit of setup. So yeah, we're not changing anything to do with the architecture of neural networks. We're just using a very standard fully connected network to kind of represent the solution of the equation. So yeah, I'm just about to get onto that actually. So yeah, the first task is to simulate the system using the PINN. And so think about our inputs and outputs. The inputs are, well, we know what the underlying differential equation is, and we know what the initial conditions of the system are. So the displacement is 1 at time is 0, and the velocity is 0 at time 0. So then we want to estimate the solution to the underlying equation. And so as I mentioned in the presentation, the PINN is going to be a direct functional approximation of the solution. So we're going to say the PINN is just a neural network that takes in the time coordinate. So in this case, it's just a single value. And it has a bunch of free parameters or weights, which are represented by theta here. I'm going to say that function that it learns is approximately the solution. And so then we've got to set up our loss function to train the PINN. And so it's composed of 3 different terms here. And the first 2 terms are going to assert that these boundary conditions are met. And then the last term is going to calculate this physics loss that I described before. So let's just go through each one. So the first one, I'm going to evaluate the PINN or the neural network at time equals 0. I'm just going to make sure that that equals 1. So I'm going to subtract it from 1, and hopefully this will be 0 if that's the case. So I'm just going to square the value, and that's my first term in the loss function. And the second term is the same for in this case for the velocity. So I'm going to say the derivative of my neural network at time equals 0 is going to try and match it to 0. So say it's starting with velocity 0. And then the final term is this physics term. So this is now a summation over many different time coordinates in the domain. So we're just going to sample. In this case, we're going to sample regularly over the domain that we're interested in. So we're interested in modeling from time 0 to 1. So we're going to sample t over 0 to 1. And we're going to evaluate the gradients of the PINN with respect to its inputs and form this residual and sum over all the different points and try and force that residual to be 0 so that the solution the network learns obeys the underlying differential equation. The other thing to note is I've got a couple of lambdas here, lambda 1 and lambda 2. So these are just hyperparameters. This is one of the many hyperparameters that you have to select for PINNs to make sure what you want is for the terms to be nice and balanced. And what I mean by that is the magnitude of one is not massively different from the magnitude of another term, such that that term just dominates the loss function and the rest aren't kind of obeyed. So it's kind of tricky to know how to select these. There's research out there that kind of has clever automated ways to do it. But for now, I'm just going to define these by hand, and I'm going to just trial and error basically for now. Then the other note, which is I already said, which is important, is we're going to use auto differentiation, and in particular in PyTorch, we're going to use torch.autocrad. And this is going to allow us to evaluate these derivatives that we need to form some of these terms in the loss function. So any questions on kind of what we're trying to retrieve before I start coding? Okay, so hopefully that makes sense. So this is the main kind of meat of the code, and we're going to try and train the PINN in this kind of for loop here. So there's a bunch of stuff that I'm going to fill in the blanks here. So you see every time it says to do write some code, I'm going to fill in the blanks. So this whole block is going to define the PINN and then hopefully train it and then plot the results as it's training. Okay, so the first thing we want to do is define the neural network. So this is very simple. We're just going to say, can you see this okay? Maybe I'll just zoom in a little bit. So we're going to say our PINN is just the fully connected neural network, which we defined above. So this is just a very standard PyTorch network. And it had 4 different parameters. And the first was the dimensionality of the input. And so that's, we're just considering time as one dimension here. So the second parameter is the dimensionality of the output tensor, which is, again, 1. We're just measuring the displacement here. And then the last 2 are just the number of hidden units in each fully connected layer and the number of fully connected layers. So I'm just going to predefine them to be 32 and 3 here. Again, these are hyperparameters that you have to test for PINNs. Okay, so the next thing we need to define are the points in the domain, so the values of time that we're going to use to evaluate these different terms in the loss function. So for the boundary loss, we just need to define a tensor that has 0 in it, because we just want to evaluate that at t equals 0. And then for the physics loss, we want to have a tensor that has a bunch of different time values in that we can evaluate it over. So we'll just call t boundary here equals torch.tensor, and it's going to be t equals 0 basically. The other thing we need to do is just for PyTorch kind of semantics, we need to make sure the shape of the inputs match the shape that a fully connected neural network expects in PyTorch, which is just the number of examples and the dimensionality of the input. And then the most important thing is we need to do this thing, which is called requires grad, and we want to set it to true. And so what is this doing? So remember, as I said in the loss function, we need some derivatives of the network with respect to its inputs, so du by dt. So what requires grad here does is it says I want to track all the operations that I do in PyTorch that involve this tensor. So there's this input coordinate or input time coordinate. So we need to do that because PyTorch doesn't automatically by default track any operations in the computational graph, unless you say that we require gradients of those operations. So this is going to allow us to compute the derivatives of the network with respect to its inputs using this input. So this is very important to do. The next array of time values we're going to need is just the ones for the physics loss. And in this case, we don't actually want a single value. We want a value across the whole, a set of values across the whole domain. So I'm just going to do a regularly sampled number of values from 0 to 1. We're going to take 30 of them. Again, just make sure that we make the shape the correct shape. And again, we're going to need gradients with respect to these tensors. So we require grad for this as well. Okay. So I think this all looks good. So basically now we're going to start writing the training loop for the PINN. So there's a few extra things that I define here. So first of all, I define what mu and k are. These are these underlying parameters of the differential equation, and we're assuming that we know them because we just want to simulate the equation in this case. So I've just picked just 2 and 20 to be the values of these d and omega naughts here. Then we're also going to create a test array so that we can plot the results of the PINN as it's training and also compute the exact solution so that we can compare it to that. And then the rest of this part is very simple torch code. So we're defining our optimizer just as you would do for a normal neural network in PyTorch. Pass it the parameters of the PINN, define our learning rate. Make sure the gradients of our computational graph are 0 to start off with. And then we're into the main training loop. So there's a couple of things that we need to define here now. Firstly, I've already hard coded in what these lambda hyperparameters, so balancing the different terms in the loss function are. I selected these by hand, but of course you would have to do that too if you had a new problem. But what we're going to write here is we're going to evaluate the boundary loss, and we're also going to evaluate the physics loss. And then we're going to backpropagate and update the weights of our network. And these are the 3 key steps that we need to do. So firstly, we need to compute the boundary loss. And so there were 2 terms in the boundary loss. One was to make sure this the solution is 1 at t equals 0, and the other one is to make sure that the derivative or the velocity of the oscillator is 0 at time equals 0. So we're going to need to write code for that. So for the first one, we're just going to run the PINN at the boundary condition. So we're going to say, what is the value of u at t equals 0, which we defined back up here, t equals 0. And so the first loss term is very simple. We can just write first loss term is, so we're just going to squeeze this output tensor of the network. So this just has one value in, but it has a shape of 1, 1 in PyTorch. So this is the shape of that tensor. So it's just going to squeeze it into a scalar. And then we're just going to subtract it from 1 and raise it to the power of 2. So if you compare this to the loss function here, we're just computing this term of the loss function. Hopefully that should make sense. Okay, so then the next boundary loss that we want to compute is the velocity of the solution is 0. And so for this, we need the derivative of u with respect to time. So we're going to say du by dt. And this is where we're going to be using the auto differentiation of PyTorch. And in particular, we're going to use this torch autograd.grad function. And this is very semantically easy to understand. Grad is just going to compute the gradients of one tensor with respect to the other using the computational graph. So what we want to do is we want to compute the gradients of u with respect to the boundary here. There's another input that it needs, which is an array of 1s. I'm not going to go into what this really means, but it's to do with the way autograd computes these Jacobian vector products behind the scenes. But suffice to say, it's computing the derivative of u with respect to the boundary point here. And then the final argument that we need to put in is this thing called create graph equals true. And so what that's going to do, all this does is says when I come up with the derivative, when torch autograd makes that derivative, I want to keep on or hold on to the computational graph that it uses to create that. And that's important because when we train the PINN, we actually want to differentiate through that graph again to update the weights of the neural network. So to get the derivative of the loss function with respect to the weights of the network. So you can see we're calling auto differentiation kind of twice to get these derivatives. So it's a very powerful kind of function call, and this is kind of this is why PINNs are so easy to train in PyTorch. Okay, and then we're just going to form our second loss term, which again we're going to squeeze du by dt, and we're going to subtract it this time from 1 because this time from 0 because we want to make sure the velocity is 0. So any questions on these, where I am so far? Because it's really important that you understand how this is working. Okay. So I'll carry on. So then there's only one other loss term, and that's the physics loss. And so we're going to use the same machinery we used up here to compute gradients of the network. We're just going to have to compute a few more gradients and combine them in a bit different way to evaluate the physics loss. We're going to say, well, actually, first we need to run the network again, this time on our physics loss points. And then we're going to copy this line up here that creates the derivative of u with respect to t. We're going to need this, but in this case, we need to change it to physics again. Like this. For the physics loss, we also need the second order derivative of this network with respect to its inputs. So it's very simple to compute that. We just copy the line again. Instead of having u here, we just do du by dt. And so this is going to create the second order derivative. I'm just going to make sure that we have du by dt here. So you can see how simple it is to compute these second order and higher order derivatives if you like. It's very flexible. And then finally, the loss function, we just combine these three quantities together. So we say, this time we're going to do a mean because we have more than one point in this physics array. And we're going to do the second order derivative here. Plus, so this is where we write our underlying differential equation. We're just going to form it from all the terms that we have. So it's the du by dt squared plus mu by du by dt plus k minus by u, like that. And then we're going to square this, and then we're going to take the mean. So very similar kind of machinery to the second boundary term, but the difference here is we're evaluating this residual of the underlying differential equation. Yeah, and then we're pretty much done now. So we have our terms in the loss function. Now all we need to do is combine all the terms together. So we're going to say a loss equals loss 1 plus, and then we're going to times it by our lambdas to make sure they're nicely balanced. Lambda 2 times by loss 3. Then we're going to take a backward step, and this is just standard PyTorch stuff to update the weights of the network. And we're just going to call the optimizer to do a step. And that should be it. So I'm going to run this, and hopefully it will work. The rest of the code here is just we're going to test the solution over our test points and compare it to the exact solution. So let's see if this is running. So it's going to run for, I think, about 15,000 steps, and every 5,000 steps it's going to make a plot. So what we've got in this plot is the exact solution, this gray curve, and the green solution is the PINN whilst it's training. And then these green dots here are the location of the physics training points that we're using, so the time values, and there's 30 of them regularly between 0 and 1. And then the red dot here is that location of that boundary point. So we're just going to use this one point to make sure the network obeys the initial conditions. And so, yeah, what you can see is the PINN is converging fairly quickly, a few thousand steps, and it's learning this oscillatory solution. So it's really cool to see. I mean, we've not really given it any training like supervised labels. We've just formulated it as a fully unsupervised learning problem. And yeah, Torch is using its auto differentiation magic to really crunch the numbers on this. Okay, so any questions on this? I think we have time to get to the next task, so I'm very keen to show you how to use it for inversion too. I'll just pause for any questions.
Could you just go over that part about it's unsupervised again, just one more time?
Yeah, so a supervised learning task is where you have examples of the solution, right? So
right.
I would give you, I know that U equals, like I'll give it a part of the solution here, or maybe a sparse number of observed points.
Right.
But we're not doing that here. I mean, we are giving it 1 point, t equals 0, but that's it. That's the only label that we give it. We're matching, you see in our loss function here, we're matching the solution to 1 and its derivative 2. But the rest, this physics term is fully unsupervised in that all it needs is some points in the domain. It doesn't need to know the solution in those points. So it's solving forward in the domain, if that makes sense. So that's what I mean by unsupervised. And that's different to,
I mean, the input is the solution, I guess. No, the input is the environment, right? The fact that, okay.
The input is the coordinates in the domain. So it's these x, y, and t values, or just t value in this case. But yeah, I can just randomly sample those. It's not like, I don't need to know the solution in advance because the PINN is learning the solution, if that makes sense.
Yeah. Okay.
Like if you compare that to like a naive way of learning simulations, which is like generate millions of finite difference simulation data and learn the mapping between the inputs and outputs.
The other example where you had pressure was the output.
Yep.
You in a similar fashion, you could update the loss function with physics, and you wouldn't need the real world example of the pressure.
Exactly.
Okay.
Yeah. So this works for any differential equation. It's just a way, you can think of it as a way to solve the differential equation.
Yeah. Okay. Fair enough.
Right. That's a good question, actually, because the next part is when we do have some data and we want to do some inverse problem. But are there any other questions on the simulation task? Okay. So we'll move on to the second task, and this is to use the PINN to invert for underlying parameters. So let's think about the inputs and outputs again. These are different to before. So in this case, the inputs are, let's say that we actually do have some observations of the solution, but perhaps they're noisy. So we're doing like an experiment and we're plotting the location of the oscillator. But what we don't know is something about the differential equation. And in this case, we don't know what mu is, the coefficient of friction. So the goal is, like, given these observations, can we actually measure can we learn, in fact, what U is? And this is a classic kind of inversion problem or inverse problem in physics. And very prevalent across many different domains of science, by the way. This is like done everywhere. So very important task to solve. So how are we going to do this with PINN? So it's the same approach as before. We're going to say the PINN is going to directly approximate the solution to the differential equation. But there's one key idea that's different. And the key idea is we're also going to treat mu as a learnable parameter when we're training the PINN. So just like theta here is a learnable parameter of the neural network, we're also going to say mu here is just another PyTorch parameter that we're going to update through gradient descent simultaneously with the thetas of the neural network. So you can think then is when the PINN's training, it's like simultaneously learning to fit the solution and also learning to to learn what this underlying parameter is. So potentially a harder optimization problem, but still quite powerful in that it might be able to learn extra parameters. So how are we going to train the PINN? So the loss function is fairly similar. We have the same physics loss term here. So this is exactly the same as what I had before, where we get random time points in the domain and evaluate the physics loss. And then I've removed the boundary loss terms here because I'm assuming we don't actually know what the initial conditions are in this case. So we just completely remove that from the loss function. And instead what I've replaced it by is a term which I call the data loss. And so this is saying I just want my PINN to match the observed values of the solution wherever I have them at these kind of j time points. So yeah, this is the data loss, and then we have the standard physics loss as well. So let me show you a picture that might help you understand this a bit more. So imagine, so this code here is just going to create some data, some noisy observational data. So I'm just sampling from that expected solution, but I'm adding a bit of Gaussian noise to it as well. So these blue points here are these observed points here that we're going to use for that data loss, the second term in the loss function. So we're just going to say the PINN needs to satisfy the physics of those regular points that I already have. And then it also needs to match these observed noisy points from this data here.
How is that loss different than something like what you mentioned earlier, the mean squared error? Is that closely resembles it? No.
Yeah, this is
data loss. This is right.
Yeah, this is exactly the mean squared error.
That's what it is. So that's what you typically use in a supervised machine learning model. Yeah. You've added the physics part in front of it. Okay.
Yeah, exactly. So this is a supervised loss. Exactly. Like you could train the PINN without the physics loss, and it would try and learn a function that fits these blue points, and we'd probably do quite well. But what we're going to find is that if you add this physics loss on top, is like you can think of it as like a regularizer that makes sure that whatever the PINN learns is like consistent with the physics, but also because this physics loss has the mu in, we can also harness it to learn the underlying parameter as well. So this is why it's way more powerful to add this in. Does that make sense?
Yes.
Yeah. So people have actually just used, when you have a lot of observational data like this, you can just use the PINN to like do a better interpolation of these points, even if you don't need to learn the underlying parameters of the PDE. Because it has that kind of physics regularizer in it as well, which is really cool. I saw an example of this for cardiovascular modeling. So you want to measure the timing of electronic signals across the heart, and you can interpolate them way better if you use a PINN rather than just a standard neural network. Right, so yeah, so we're going to try and train the PINN to fit these points and also learn mu as simultaneously as well. So we've got another training loop set up here. And it's going to look very similar, to be honest, to the one before. There's just a few key changes that we've got to make. So first, we've defined the neural network again. We've defined our physics points. In this time, we don't need our boundary points because we don't have a boundary loss. So the first thing to do is we have to say, actually, we don't know what mu is here. So we're going to treat it as a learnable parameter that we don't know in advance. So how do we do that in PyTorch? So this is how you create a learnable parameter in PyTorch. One way to do it is you can go into the neural network library and just define a parameter here. And we just initialize it to be 0. And we also make sure that it requires grad so that we can train it, as I was describing before. So this is just basically a tensor that we've wrapped around this parameter so that the optimizer can use it behind the scenes. Okay, and then another thing we need to do is to define our optimizer. And before we just gave the optimizer, if I copy and paste the code from the first bit, you see we just gave the optimizer the PINN's parameters. What we need to do here is we need to also give it mu as a parameter that the optimizer is going to change. So what we have to do is we just turn this, this is a generator that we turn into a list, and we're just going to add it to, we're going to add mu to that list as well. So this is going to make sure that the optimizer updates mu alongside the parameters simultaneously. Then we compute the physics loss. It's the same code as we had before. I haven't changed anything with this. But the last thing we need to do is compute the data loss. And so what we're going to do here is we're going to run we're going to run the PINN over the observed time points. And this is just, this observed time points here is just computed up here. And then we're going to create our data loss, which is just the mean squared error that we were talking about before. So we're going to do a mean over u minus u observed, like that. And we're going to just do the mean squared error. Combine the two loss terms together, run a backward step, and then optimize. And it's really cool that Torch is going to be able to handle both the weight arrays of the neural network and also this single scalar parameter. And it's going to optimize it together in the gradient descent loop. And we really don't have to worry about doing those gradients by hand or anything really. It's Torch is a very powerful language. The last thing we'll do is we have this list. We're going to create a list here just to record the values of mu so that we can plot its convergence over the training step. So we're just going to append that, and we can just take the scalar value here. Cool. So we've set up the optimization loop, and we're just going to plot the result again. And at the end, we're going to show how mu has evolved over training step, and hopefully it will converge to the true answer that we know, which is 2 times d here. So let's see. Okay, so we've got an error here. So torch.0. So we need 0, I think. Yeah. Okay, so PINN starts training we're plotting the noisy observations here in the PINN solution. So what we're hoping is the PINN starts to fit those observations a bit better as it trains. But remember, as it's doing this, it's also optimizing mu, so it's a harder optimization task than it was before, arguably. So we just wait for the, again, it's going to run for 15,000 steps, and you see it's doing a really good job. And what's interesting is it's not overfitting to the noisy points. It's still fitting a nice smooth line across, and that's because that physics loss is really regularizing the solution. So that's really cool to see. Yeah, and you can see after 15,000 training steps, it's pretty much got the solution. And so what we're plotting here is the value of mu over the training step and comparing it to the true value. You can see once it's nailed the solution, it also has learned the value of mu. So I'm aware that it's 6 o'clock now, so I don't have time to go to the last section. But if you're interested in the kind of scaling to higher frequencies, definitely recommend having a read of that. But hopefully what I've shown you, if I go to the very top again, is that, yeah, it's fairly simple actually to code a PINN from scratch in PyTorch. We take advantage of the autodiff features. We've shown that you can do a bunch of different scientific tasks, and hopefully you can go away and adapt this to your needs in the future. So yeah, maybe there's not time for questions, Jousef, but otherwise it's been a pleasure.
Thank you so much, Ben. Really nice tutorial. We still have time to take some questions because that's the only session for today.
Okay.
Guys, any questions to Ben?
Yeah, I have a question. So maybe to the previous example you showed, the 2-dimensional wave propagation. I have a question. Do you know, is it possible to use this method to simulate the 3-dimensional sound propagation, for example, like in the room? And do you know how long would it take to predict a single value?
Yeah. So yeah, people have tried. So in theory, you can. The PINN works for any. In theory, works for any differential equation for any number of dimensions of the inputs and the outputs of the solution. But in practice, you come across some scaling issues that I didn't get time to talk about. So especially when you go to 3D, 4D, including like 3 spatial or 1 time dimensions, you get an exponentially increasing number of physics coordinates that you need to use to train the PINN. So you've got to sample densely over the entire domain, and as the dimensioning increases, that becomes a real issue. So it is possible, but typically you have to restrict the domain or think of more kind of intelligent ways to do the sampling. For example, you can have like sampling out in time, so you can just sample like early times to start with, and then like sample later times as training progresses. But it's a tricky problem. I mean, the other issue is probably as the solution gets more complicated, the size of the neural network also has to increase as well, and so. Yeah, these are issues that are difficult.
Yeah, thank you.
So we have a paper out at the moment actually where we combine domain decomposition with PINNs, and so we actually split the domain into lots of little pieces and have a small neural network in each, and then we train them to communicate with each other, kind of like finite element methods in a way. And it can improve the kind of convergence of these kind of high frequency, large domain problems, but yeah, still very much an area of research.
Interesting. If you could send us some resources or me some resources, Ben, I would be happy to share them with the audience.
Yeah, that sounds good. Yeah.
How do you see the future of PINNs? Because I feel I've met some guy in Munich who knows the PINN gurus, so to speak.
Yeah.
And they're not doing so much research in PINNs anymore. So they worked on deep O-nets and PINNs, but now they're moving a little bit away from PINNs. Why is that? Is that not very promising, or?
Yeah, it's tricky. I mean, there has been an awful lot of research since the first PINN paper. If you look at the works that cite it, it's been amazing. There's been like people have used like turned it into like Bayesian PINNs. They've done equation discovery, which I didn't get onto with PINNs. So there's been a lot of work that's they've done like PINNs using a weak formulation of your PDEs, etc. So I would argue there's a lot still to kind of learn, especially these kind of theoretical properties of PINNs we really still don't understand. But yeah, I think people are coming up against these like scaling issues, like the fact that they take a long time to solve or to train the neural network if you just want to do a pure simulation. And how do we overcome that? That's still a challenge. And so yeah, there's and I think what we're also seeing is in this field of scientific machine learning is a trend towards these kind of like more hybrid techniques where PINNs are one of them, but you can make PINNs even more hybrid in a way by combining it more tightly with like finite difference, finite element methods. For example, like using this domain decomposition that I was talking about. So yeah, there's to some extent, it's people just kind of following the next hot area, but there's a lot left to learn about them.
Yeah, when it comes to practical applications, it seems that a lot of when you look up PINNs, it seems that you only find like solving the Burgers equation, for example. Yeah. Is there like any practical applications that you could think of where they made use of PINNs, or the advantages of PINNs?
Yeah, so for sure that I was thinking, where I think the most powerful at the moment are these, what I would call messy problems, where you want to do forward simulation and inversion at the same time. And so, for example, I can send some papers later. There's one where they're designing kind of waveguides for nanomaterials. So for example, if you want to make a certain like array invisible, like a cloaking device, for example, you can use the PINN to invert for the structure of the device itself. There's also this cardiovascular example where they were trying to get more precise measurements of the time it takes for the electrical signals to go across your heart. And you can interpolate those like noisy, sparse measurements you have from doctors to do that in a better way. So there are a select examples, but yeah, these kind of messy problems where you have some data already.
But it isn't 100% necessary to know the underlying equations for that problem. For example, if we think about a practical application such as a crash test, for example, would you be able to use PINNs for that application?
Yeah, so I think you can learn the underlying equation as well. So like I showed already in that example, you can learn like one coefficient.
Mhm.
You can also learn more complex things, like you can, for example, you can query all of the gradients of the network and then combine them, like do a sparse regression over different combinations of those gradients to try and learn like how the terms interact with each other, to actually learn the entire PDE. There was a paper that just came out recently in Nature that was doing that.
Oh, nice. You should actually share that with us, because I will have a look at
Yeah.
that. That would be interesting.
Yeah, I'll show you. Yeah.
Nice. Ben, thank you so much for taking your time and doing this awesome tutorial. Cool. Then I hope to see you on the podcast, Ben, as mentioned earlier on. We talk a little bit about PINNs, and thank you so much, and hope to see you in another session soon.
Thank you very much. It's been a pleasure. Nice to meet you.
Bye-bye. Bye-bye.
Bye.